perhaps one of the most complex issues related to cost-benefit analysis is the idea of the time value of money. So what is the time value of money? Well, money has a time value because we can invest it and expect that over time it'll grow, which means it'll earn a positive rate of return for that deposit. If you put money in the bank today, you expect that sometime in the future when you take that money back out, it'll be worth a little bit more at least than what you put in. If you put $1 in the bank today and you earn a 10% interest on that dollar, when you take it out of the bank in a year, it'll be worth $1.10. $1 today is typically considered worth more than $1 received tomorrow. This represents an important concept called opportunity cost. And what that means is that the sooner we receive money, we can use it to earn interest or invest it in something. So if your friend says, "Can I borrow $1?" you have to weigh, what can I earn back on that dollar if I keep it and invest it versus giving it to my friend essentially for free. If your friend has offered to give you a 10% return on that $1, then you can determine if there are other ways that you can earn more than 10% on that dollar. If not, then it's a good investment to hand it to your friend. If, on the other hand, your friend is a bit of a mooch and would like to take that dollar and return it tomorrow or the next day or whenever with no interest paid, then this represents a distinct opportunity cost. That is, handing over that dollar to your friend who's not going to pay you anything for it is a lost opportunity to make money on that dollar in some other way. Perhaps you have a better friend that's willing to pay interest, or maybe you can put it in your bank account and earn a little bit of interest on that, or invest it in stocks. All of those other things you could have done with the dollar are lost if you hand it to your friend. So postponing the potential investment value or the time value of that money another day is a lost opportunity. So as a result, we'll typically value money that we receive sooner as a return from an investment than money that we receive over a longer period of time. That's a fairly high concept. So how do we use it in the real world? Well, the time value of money is used in a number of different ways, anywhere from evaluating what a stock should be worth to financial analysis of individual firms. That is, if I invest in this firm, how long will it take me to get paid off? And the longer it takes to get a payoff from that investment, the worse the investment typically will be. And in a more applied fashion and more relevant to what we're talking about, at the end of the day, the time value of money is the determining factor on whether to accept or reject decisions for planning projects. And there's many other ways that we use time value of money. Pay attention now to the news, because what you'll likely be hearing is the possibility of a negative borrowing rate in New Zealand. And what this essentially means is that the volatility of the economy has made it so parking your money in a bank or somewhere where it can just collect interest is so safe compared to the potential losses you might face in other investments. They expect some large banks are willing to pay to have money safely stored away. And that in itself is infused with the idea of the time value of money. So to better understand TVM, there's a few things we should get out of the way. The first thing is some terminology. So we talk about the time value money at different phases. The first phase is the present value. And the present value is the amount of money that you have today or the current value of a future investment. So we can think of this whenever we talk about inflation. We talk about something 20 years ago that only cost $1, but today it costs $1.50. And the reason it costs more money now is inflation. The value of that dollar has decreased over time. So you need to pay more dollars to buy the same amount of goods now that you could with fewer dollars in the past. And so that value of money can move forwards and backwards. So comparing a dollar spent today to a dollar spent in 30 years or 30 years ago is not the same thing. When we conduct cost-benefit analysis, our main goal is to get all of the cash flows into one single time, whether it's present value or in another case, future value. That is the amount of money that something is worth in a future period of time. So what's a period? A period in this case is simply a length of time. It's often measured in terms of a year because that's when we typically assess things like interest rates. No doubt you've heard the term APR, the annual percentage rate. Often that's broken down into smaller increments by month or week or day, but at the base is a year-long term. So we often say a year is our base period, but it can be anything really. And then finally, interest rate, and this should be pretty straightforward to most of you. It's the compensation you have to pay to a lender for the use of their funds expressed as a percentage for a period. So to take out a loan, you borrow $10,000 from a lender and you say you'll pay 10% each year for 10 years. That's how the interest rate is structured. And when we talk about lender, it's not just a big bank, but every time you put your money in the bank is then using your money to fund loans to other people. So while you may be a saver in a bank account, you are also at the same time a lender, and your return that you get on your bank account is just a cut of the interest rate that the bank is getting for lending out your own money. And to better understand how the time value of money equations that we'll see in a minute work, we should break down the nomenclature of TVM equations based on the variables that we commonly see in those. F will represent future value, P will represent the present value, I is the interest rate for the interest period, while R denotes the nominal interest rate or the percent paid per year. N sub Y is the number of years, and N is the number of interest periods. And we'll see how these work in just a second. So let's talk about a few basic approaches to calculating interest, which at the root is how time value of money functions. So simple interest is really just the future value of something. So the most basic calculation used in time value of money is simple interest. And to know what simple interest is simply to know what the future value of some investment might be. We can do this by first setting F equal to 1 plus N times I, N representing the number of interest periods and I representing the interest rate for the period, and multiplying that whole thing by P, the present value. Slightly more complex, but the way the real world typically works is compound interest. With compound interest, we can work out the future or present value, and it can be inverted to give a present value associated with a discount factor, and we'll talk about discount factors in just a moment. What this also allows us to do is, using a financial term, capitalize the interest paid in a period to set the new future value of that investment. So let's say you invest that dollar today in a bank account earning 10%. At the end of the first year, that investment will be worth $1.10. As the next year proceeds, using simple interest, you would simply earn another 10% on that original $1. Using compounding interest, and this is why investments are so worthwhile in retirement funds and other investment instruments, in the second year we'll earn a 10% return on that $1.10 that was in the bank account. So with a dollar investment, it might seem small, but with simple interest, at the end of 2 years, your investment would be worth $1.20. With compound interest, your investment would be worth $1.21. You pick up an extra penny. But the year after that, your compounding interest will be based on that $1.21 compared to the $1 under simple interest. So the difference between simple and compound interest each year will grow exponentially. So the equation for compound interest simply moves the N variable for the number of interest periods outside the parentheses and makes it an exponent, which means it'll have exponential growth. So using compound investment, the future value of some present number is 1 plus I to the power of N times P, the present value. Now let's get back to that nominal interest rate. It's just simple interest when the period is not 1 year. So all we need to do to figure this out is multiply I, the interest rate for an interest period, times M, and in this case, M is the number of periods per year. So there may be an investment where you earn 10% per month. So this is common when you look at credit cards or your bank account, where interest is being applied on a monthly basis rather than an annual basis. So some interest rate is being applied multiple times throughout the year. The effective interest rate is simply the compound interest when the period is not 1 year. And so the equation is a little more complex. It's I sub EFF for effective interest rate, and it's equal to 1 plus R, the nominal interest rate, divided by M, which is the number of periods per year, with the exponent outside the parentheses of M minus 1. We won't use that too often, but it's there just for the record. So you saw my handwritten examples of simple and compound interest. Now we'll just use some PowerPoint-based examples so that you don't have to try to decipher my rather sloppy handwriting. Let's differentiate between present and future value, or the way we can move forwards and backwards between these values. So let's say we want to determine the present value of an investment in the future. So that present value really is, if there's some amount of money in the future, what is the purchasing power of that future money in today's terms? We know from the ideas around TVM that past dollars were worth more or had higher purchasing power than today's dollars. And in the future, to buy the same amount of stuff we do now with $1, we'll need more than $1 to make that same purchase. So as an example, we might ask a question like, if there's a $10,000 lump sum payment made to your agency 2 years from now, what is the present value of that payment if we can earn 10% interest on that payment? Or in another case, we might want to determine the future value of a present dollar investment. That is, if we have $10,000 left in the bank today for 10 years at 3% interest, what's that worth at the end of 10 years? So let's contextualize this a little bit with an example. Say you have a student loan, a pretty common form of debt or investment. Let's say as an undergraduate, you take out a $10,000 loan at the start of your college career in August of 2018. Say that loan then has a 5% interest rate, which will be applied to the principal of the loan until you graduate in August of 2022. That's 4 years of interest. When you graduate from college, how much is that $10,000 loan going to be worth to your investor, not to you? How much is it going to cost you? Well, we use a future value formula or a compounding interest formula. So we want to know the future value of that investment, that's F, and we set that equal to 1 plus I, that's the interest rate paid, and we exponentiate that with the number of periods that interest is applied times that original cost, or the amount we took out. So let's bring that forward a little bit, and that future value is 1 plus that 5% interest, so 0.005. We're paying this once a year for 4 years, so that's 4 as the exponent outside the parentheses, and then we multiply that by the $10,000 we borrowed. So the amount of money we owe for borrowing $10,000 for 4 years at 5% interest has grown from that initial $10,000 investment in 2018 to $12,160 in 2022. It's cost us $2,160 to borrow $10,000 and hold on to it or hand it over to your college for 4 years. And that's how time value of money works. As a lender, the entity that loaned you that money had to evaluate whether this was a worthwhile investment for them. And so they evaluated whether they could find a return greater than 5% or a return that was slightly less than 5%, but more likely to return, but less likely to default. And in giving you that $10,000, they decided that there was no greater opportunity cost associated with that lending, that your $10,000 loan was the best investment, that the costs of that investment were outweighed by the benefits. There's a few different ways we look at these investments or these projects over time. One is an annuity, and perhaps you've heard of this in some way or another. It's really just a series of single payments that we denote as A made at a fixed time period. So an example of this is common installment loans. This is student loan repayments, which we were just talking about, a mortgage payment, a car payment, or a bond repayment. You know how much you're going to pay. Sometimes there's a balloon payment at the very end, but month after month you're making the same payment to pay down both the principal and the interest of that amount borrowed. That's an annuity, an annual payment over a period of time. It also assumes that there's some sort of periodic compound interest and a payment at the end of the first period. So to determine the total cost in the future of that annuity, or the value of that annuity at some future time, we use what's called a discrete uniform series compound amount factor. That's a mouthful, but at the end of the day, it's much like a compounding interest formula. So we look at the future value of something, and that's set equal to the annual payment that we make times 1 plus the interest rate to the power of the number of times we make that payment minus 1, and all of that is divided by I. So based on the amount of the payment that we make and the interest rate known and the amount of time that we're making that payment, we could determine how much that series of payments will be worth at a future date. If we want to know what the present worth is of an annuity, let's say we have $10,000 that will be paid to us at some future date, and we want to know what's that $10,000 worth to me right now, we use the formula for the present worth of an annuity, and that's P for the present value set equal to F, the future value, divided by 1 plus I, the interest rate, to the exponent of N, the number of interest periods. Let's use the same example to add a little more context. If we go back to that student loan payment, so we know that the total loan value in the future in 2022 is $12,160. So let's figure out what that annuity or that payment will be. Let's take our student loan from 2022 on. Now we know we're going to have to pay back that student loan at some point. So starting in 2022, we're going to make payments, and that loan is now gone up to $12,160. That's the amount we're going to have to pay back starting in 2022. So while we pay down that loan, not only are we going to have to pay the original principal plus the interest that accumulated, or the capitalized interest of $12,160 total, but over the payment period, we're also going to have to pay interest on that total amount as we pay it back down. That's the same way a car loan works. In essence, you're borrowing, let's say, $10,000 today. The payment that you make on that $10,000 car loan represents a payment of both the principal, that $10,000, plus the interest applied to that principal over the period of the loan. So using a 5% interest rate, let's try to determine what the loan payment will be if it's paid off over 10 years of monthly payments. Well, we won't do this by hand, but I will tell you that the loan payment is going to be about $128.98. So a couple of things are happening every time you make a payment on that loan. The principal is being charged an interest rate each month, but each payment you make pays interest and lowers the principal so that the interest is less. You're paying 5% interest on a declining principal amount. So over time, with a fixed payment, the payment shifts from mostly paying interest to mostly paying principal as time goes on. Think about this in terms of a home loan. When you first borrow that money, it's a little bit painful if you look at your statement. The majority of the payment that you're making is not going to pay down the principal of that loan and thus build equity in your house. Rather, it's going to pay the interest. But over time, as you bite off more and more pieces of that principal, more of your payment each month starts to go towards paying down that principal. So over time, as that loan begins to mature, the vast majority of your payment is quickly paying down that principal and very little is going to interest. So how do we really calculate the future value of something? That's certainly a key component of the cost-benefit analysis process. If we don't know what the future value of something is, then how do we evaluate its worth over time? So suppose that you have, let's say, an extra $100 today that you want to invest for just 1 year. if you can earn 10% interest on your investment, how much will you have in, let's say, 1 year? Well, again, this is a pretty simple process. We talked about it earlier in terms of $1. Let's break it down into its simplest terms so we can all kind of be on the same page here. $100 today. It's invested for 1 year. It earns 10% interest. What's laid out here is an investment timeline, and it helps us determine when payments are made, when interest is applied, and what the future value of something will be. So at time 0, the initial investment, we subtract $100. That's $100 out of our pocket and into some investment. So the question is, at the next notch here, the next period, 1 year, what is that $100 worth? So we can break this down into the future value formula. And so we'll denote this as FV1, the future value in 1 year. And this is going to be equal to that original investment, or the present value, P, that's the $100, times, and we'll use the simple interest rate formula here again, 1 plus that interest rate is 0.10 or 10%. So in 1 year, as you can probably do this in your head, that investment is worth $110. Suppose at the end of that year, though, you decide to extend your investment period. You're going to add 1 more year to that investment. So how much is it worth at the end of year 2? Well, now we have a different situation. Now we have compounding interest, as I talked about before. And so our future value in year 2 equation is FV sub 2, which is equal to 100 times that first period of investment, 1 plus 0.10, and then the second period here in the second set of parentheses, 1 plus 0.10. And if we put those together using the order of operations, what happens is 100 is multiplied by the first set of parentheses. This is going all the way back to algebra, so if you don't remember this, that's totally fine. 100 times that first parentheses, you get $110. $110 times 1.10, that second set of parentheses, then comes out to be $121. So we can simplify this in our second equation there at the bottom as the future value in year 2 is equal to 100. And since we have the same interest rate applied 2 years in a row, we just take 1 plus 0.10 and square that, or exponentiate by n number of periods, which is 2. And that's our compound interest formula. So that's how we derive really our compound interest formula. It's just applying this same interest rate the number of years that it's going to occur. So if we generalize that future value formula, we can see that the future value of an investment is the exact same formula as the compound interest rate. That is, reorganizing this pattern that is developing, we can generalize the future value calculations as the future value in some number of years, so sub n, capital N, is equal to the present value of the investment multiplied by 1 plus the interest rate to the exponent for the number of years of that investment. To find that future value in the year 3, we set it equal to that initial investment of $100 times 1 plus 0.10, that's the 1 plus the interest rate we earn each year, to the exponent of the number of periods, that's 3 years, and that's equal to $133.10. And again, we can see this dividing line between this and simple interest. Under simple interest, just doing a quick calculation in your head, you would get $130. So in 3 years, we have $3 more than we would have under the simple interest rate. And as time goes by, this continues to grow and grow. And how much does this grow? What is this difference? Let me pull an example from the United States, before it was the United States. On November 25th, 1626, Peter Minuit perhaps made the greatest investment of all time when he purchased, and I'm kind of air quoting here the word purchased, the island that would come to be known as Manhattan, New York, from the Lenape Native Americans for $24 worth of beads and other trinkets. $24 in 1626. So was this a good investment for what would later be called the Indians? So if we do the simple math, this happened 394 years ago. So if they could earn a fairly low 5% interest rate each year, in the year 2020, how much money would they have? How much would that $24 be worth if they were able to continually invest it? Taking that $24, we just multiply it by 1 plus the interest rate, which comes out to be 1.05, and then we exponentiate that by the number of years, 394. And if we do that, it comes out to be $5,355,438,979 in current dollars. So $5 billion for the entire island of Manhattan. Maybe not the best investment, but what if they could earn double their interest rate? The historic rate of return on the stock market and many other investments hovers around 10%. So if they could have earned that 10% interest, how much would compounding interest make a difference in this case? Well, we take that $24 and we multiply it by the 1.10, the 10% interest, and we raise it to the power of 394 for the number of years. That comes out to be a mere 488,572,697,559,164,000. So take your $24 now and find a 10% investment and do whatever you can to live for the next 400 years. It'll be well worth the investment. So we've been looking at the future value of money. Let's bring that back and say we want to know what the current value or the present value of some future amount of money is. We talked about this a little bit, but let's see the formula quickly in one more context so we can turn around our future value formula and really determine what amount needs to be invested today in order to achieve some future value. So one way we look at this is, how much money do I want when I retire? So this equation can be done as the present value is equal to the future value in some number of years divided by that compound interest rate, 1 plus I to the power of n. Putting that together based on the rate of return for some investment and how much money you want to retire with, you can figure out what you need to be investing today to get that amount of money.